Welcome to Lab 1 Charged Tapes from Physics 2. I am Jason McCabe. So here's our content overview. We're going to be doing an introduction, fundamental principles, and all of these categories as we go through the lab. So, introduction. The purpose of this lab is to observe the interactions and amount of charge on manually charged piece of tape that we did by hand, and the materials that you'll need are clear Scotch tape, 2 objects, GlowScript software, and the results. The charge that was determined to be on each piece of tape was 2.684 coulombs to the times 10 to the negative 8, and the number of electrons was 1.6774 times 10 to the 11th electrons. So some fundamental physics principles that we need for the lab. Newton's second law shows that the sum of forces is the mass times the acceleration of the forces. Coulomb's law, which shows that the difference between the two charges creates a force, and that force is equal to 1 over 4 pi epsilon naught times the two charges over the distance squared in the direction of the distance. Gravitational force near the surface of Earth is just m's times g, which is what you get when you simplify that expression right there. So, initial conditions. The tape's mass was 0.00015 kilograms, the tape length was 0.21 meters, the tape width was 0.02 meters, the tape's area was 0.004 meters squared. An atom's area is as shown right there, which is 1 times 10 to the negative 10 squared, and the number of atoms was found to be 4 times 10 to the positive 17 atoms. So the observed model, this is when we did the experiment in person, or online, I guess. I did the experiment. So here it shows what we're supposed to see. So this is us lifting the negatively charged piece of tape, or the charged piece of tape, towards the other charged piece of tape and how it's supposed to repel. This was the charged piece of tape that was repelled. This is the charged piece of tape that did the repelling. So here's calculating how many electrons were needed for this. So we can calculate the gravitational force. We then calculated what was needed to be the electrical force. The electric charge was found from that formula. And then the number of electrons lost was just the charge of the tape divided by the charge of electrons. It shows how many electrons we used. So for our first computational model, we can see what was the magnitude of charge on one piece of tape as calculated by the first computational model, where each tape is a single point charge, and we can see that the charge found was 8.49138 times 10 to the negative 9 coulombs. And here's the rest of our calculations with our constants. The constants, 1 over 4 pi epsilon naught, the distance, gravity, etc. Here's our second one. So this is a bit more complicated because we're actually creating a computational model that shows the difference in if it was like multiple charges placed along the tape as opposed to just being 1 point charge. So that's why it's a bit more complicated. We also use the observed items, so like the mass of the tape and the charge that we calculated. And so here we're printing and drawing all the arrows, and here we can actually see the arrows, so we know that the force of gravity has to be less than the force of the electric force on it because the tape lifted up. And that's good because we can see that. We can see that the white arrow, which represents the electrical force, is larger than the yellow arrow. So here are some assumptions. We assume that air resistance and friction are negligible. We assume that the long tape is a point charge for model 1, and we assume that the tape was evenly distributed for the second model. Some errors. It could be unequal, the distribution of the charge along each piece of tape when we did it. We can also have loss of charge due to environment and handling of the tape, like when we were actually doing the experiment. And our discussion, what if electrons and protons had inverse charges? So if a proton was negative and if an electron was positive, that actually wouldn't change anything because they would still be the same charge no matter which charge they were. And because they were still the same charge, they would still repel, and we would still get the kind of floating effect that we get between the two charged pieces of tape. And what is the difference between the two models? So the first model is a little less accurate because it's kind of like a perfect situation where you have just 2 point charges as opposed to it being like spread along the piece of tape like we saw in the second model. So the first model is going to underestimate the needed charge because it's perfect and there's less distance between each of the charges. Thank you.